Welcome to The Explainer. So today we're taking something that has frankly terrified high school students for generations. You know, that giant, intimidating chart of letters and numbers, and we're going to transform it into a perfectly logical treasure map. If you've ever looked at the periodic table and just felt completely overwhelmed, well, get ready, because by the end of this, you're going to see it for what it truly is, the ultimate cheat sheet to the universe. Picture this. You walk into a massive, sprawling library, and thousands of books are just dumped all over the floor in absolutely no particular order. Now try finding one specific textbook. You'd literally spend hours, right? But if those books are categorized by subject and then by author, you could find it in seconds. Well, chemistry is exactly the same way. We currently have 118 known elements. Trying to memorize the chemical behavior of every single one individually? Completely impossible. We need a system. We need classification. Here's our roadmap for today. We'll quickly cover the need and history of classification, the structure of the modern periodic table, electronic configuration and blocks, trends in physical properties, and finally some of the most fascinating exceptions in chemistry. Let's jump right in. Section 1. The need and history of classification. Let's trace the historical breadcrumbs left by early chemists who were desperately trying to make sense of all this elemental chaos. Our journey starts way back in 1789, when Antoine Lavoie sorted the 33 known elements into basic categories like metals and gases. Fast forward a few decades, and scientists like Dobereiner and Newlands were trying to group them by triads and octaves. But the real game-changer hit in 1869 with Dmitri Mendeleev. He arranged the elements by increasing atomic mass into rows and columns. And what made Mendeleev a true genius was his confidence. He literally left empty gaps in his table, boldly predicting the existence and properties of elements that hadn't even been discovered yet, like gallium and germanium. But, his mass-based system wasn't entirely perfect. The crucial turning point arrived in 1913. Henry Moseley was running X-ray experiments and discovered a fundamental truth. An element's true identity isn't defined by its atomic mass, but by its atomic number, the number of protons. This brilliant little shift instantly fixed the lingering issues in Mendeleev's table, like figuring out exactly where to put isotopes, which have different masses but the exact same chemical properties. Moving on to Section 2, Structure of the Modern Periodic Table. With Moseley's discovery, everything just clicked into place. Okay, let's look at the actual framework of the long-form periodic table we use today. Check out these digits: 2, 8, 8, 18, 18, 32. We call these the magic numbers. The periodic table has 7 horizontal periods and 18 vertical groups. Elements in the same vertical group share very similar properties. So if you pick an element, let's say lithium at atomic number 3, and you want to know the atomic number of the element directly below it in that group, just add the magic number. 3 plus 8 gives you 11, which is sodium. Add 8 again, you get 19, potassium. It's basically the ultimate cheat code to navigating the vertical columns. But what happens when we discover a brand new element? Because in the past, scientists from different countries would literally fight over naming rights, creating massive confusion across the community. To stop these naming wars, a really elegant, temporary 3-step IUPAC naming system was created. You just take the atomic number, say 105, and translate the digits into specific roots. So un for 1, nil for 0, and pent for 5. Slap an IUM on the end, and boom, unnil pentium. It stays that way until everyone can officially agree on a permanent name. All right, Section 3, Electronic Configuration and Blocks. An element's atomic number doesn't just give us a name, it gives us its electronic configuration, which acts a lot like a precise GPS coordinate, placing it into distinct neighborhoods on the table. The final destination of an atom's very last electron completely defines its block. If the last electron lands in an s orbital, it lives on the far left in the s block. If it lands in a p orbital, it's over on the right in the p block. The d block forms that transition bridge right in the middle. And those 2 detached rows at the bottom, they're just the f block elements, placed down there simply to keep the table from becoming ridiculously wide. Pretty practical, right? So the key takeaway here is you can pinpoint absolutely any element just by looking at its electrons. The highest principal quantum number, or n, is your master key for finding an element's horizontal period. If an element's highest n is 3, well, it lives in period 3. Meanwhile, the number of valence electrons, the ones living out in the outermost shell, dictates its vertical group. Which brings us to Section 4, Trends in Physical Properties. Now that we know the neighborhoods, let's see how this builds into predictable physical terrain across the entire table. Think of an atom's size, its atomic radius, like a game of tug-of-war. As you move from left to right across the period, we're adding more protons to the nucleus, but the electrons are staying in the exact same shell. This stronger positive nucleus easily wins the tug-of-war, pulling the outer electrons tighter and actually shrinking the atom. But when you drop from top to bottom in a group, it's a totally different story. You're adding entirely new outer shells, making the atom expand significantly. It's kind of like layering on thick winter coats. And this whole size-shifting magic absolutely applies to ions too. When an atom loses an electron to become a positive cation, it's basically dropping baggage. The nucleus now has fewer electrons to manage, so it pulls the remaining ones much closer, making the cations slim down. Conversely, when an atom gains an electron to become a negative anion, it bulks up. The extra electrons crowd the space, causing them to strongly repel each other and swell the radius outward. Now, what if you have different atoms or ions that have the exact same number of electrons? We call these isoelectronic species. Take oxide, fluoride, neon, and the sodium ion. They all have exactly 10 electrons. So are they all the same size? Nope, absolutely not. The one with the highest atomic number, in this case sodium with 11 protons, has the most pulling power. It will yank those 10 electrons the tightest, resulting in the smallest overall radius. Okay, let's switch gears to ionization enthalpy. I like to think of this as the energy price tag for stealing an electron from an atom. As you move right across the table, atoms get smaller, and the nucleus holds on to its electrons with a much stronger grip. Because of that, the price tag skyrockets. It takes way more energy to steal an electron. But as you move down a group, the atoms get massive. Those outer electrons are sitting so far away from the nucleus that they're incredibly easy to pluck off, meaning a much lower energy price tag. On the flip side, we have electron gain enthalpy. This is the energy an atom happily releases when you hand it a new electron. Elements on the far right, especially the halogens in group 17, are absolutely desperate for just one more electron to achieve a perfect, full outer shell. When they finally grab one, they release a massive amount of energy, which in chemistry terms is represented as a highly negative value. And that leads right into electronegativity. Now, my favorite way to think about this is the pizza analogy. Imagine two siblings supposedly sharing a pizza, but the older sibling keeps slowly pulling the box closer to their side of the table. In a chemical bond, atoms share electrons, but highly electronegative elements like fluorine are definitely that older sibling. They selfishly hog the shared electrons, pulling them closer to their own nucleus. And this tendency predictably increases as you move up and to the right of the table. Finally, Section 5, Fascinating Exceptions of Chemistry. Because, every great map has its mysterious, uncharted zones. Chemistry is totally famous for its rule breakers. For instance, we established that it gets harder to steal an electron as you move left to right. But look at nitrogen and oxygen. Nitrogen stubbornly holds onto its electrons much harder than oxygen does. Why? Well, nitrogen has a perfectly half-filled 2p orbital, which creates this special state of Zen-like stability. Oxygen, on the other hand, has one extra electron crowded into that orbital, causing repulsion, so it actually wants to lose that electron to reach nitrogen's stable state. We see another major exception with electron gain enthalpy. You'd logically think period 2 elements like oxygen and fluorine would release the most energy when gaining an electron. But actually, elements right below them in period 3, like sulfur and chlorine, release way more. This happens because oxygen and fluorine are incredibly tiny. Their orbitals are basically cramped studio apartments. Forcing a new electron in causes massive repulsion. Meanwhile, sulfur and chlorine have much larger 3p rooms, so they can comfortably accommodate a new electron without all the drama. In fact, almost all the elements in the second period, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, display what we call anomalous behavior. They're basically the first kids in the family, and they always act just a bit weird compared to the rest of their group members further down the column. This is primarily due to their exceptionally tiny size, intensely high electronegativity, and the fact that they're completely restricted to a maximum of 4 valence orbitals, which strictly limits how they can bond. And as we start to wrap up, notice how beautifully an element's oxidation state, that's the charge it acquires when forming a compound, ties directly back into its group number. For the left side of the table, the oxidation state is exactly equal to the number of valence electrons. They happily give those up. For groups 15 through 17 on the right side, elements prefer to gain electrons to reach the magic number 8, so their common oxidation state is usually 8 minus their valence electrons. The table is literally doing the math for you. Which brings us to the ultimate question. Right now, our map is totally full up to element 118, oganesson. But the universe is vast, and science never stops. When element 119 is finally confirmed, based on the GPS electronic coordinates and the magic numbers we've decoded today, where exactly will it sit on this map? I'm going to leave you to ponder that puzzle. Keep using the table as your guide, and I promise the chemical universe will always make sense. Thanks for joining me on this explainer, and I'll catch you next time.